Hi everyone, we are Roman and Katherine and we are going to present chapter 6, which is called Network Layer. This video is focused on network layer protocols, communication between networks, and routers. Network layer is also called Associate Layer 3 and it's responsible of providing services to allow end devices to exchange data across the network. To accomplish this, there are four basic processes. The first one is addressing end devices. This means that each end device must be configured with a unique IP address, and this is principally for identification on the network. The second one is encapsulation. Network layer receives a protocol data unit from the transport layer, and it adds an IP header information that includes IP address of the source and IP address of the destination. After this process is done, the PDU is now called a packet. The third process is routing, where the packet is processed by a router, and this router selects paths to direct packets toward the destination host. And the last one is the encapsulation. When the packet arrives to the network layer of the destination host, the host checks if the IP header matches with its own, and then it removes the IP header from the packet, turning into a PDU for transport layer. In other words, we can say that the encapsulation process is just removing headers from upper layers. The network layer has several protocols, but the most used are Internet Protocol version 4 and Internet Protocol version 6. Other protocols include Novel Internetwork, Packet Exchange, AppleTalk, and Connectionless Network Service. Now we're moving to the characteristics of the IP control. IP is a network layer service that is implemented by the TCP/IP protocol suite. This protocol was designed as a protocol with low overhead due to the fact that it provides only the functions that are necessary to deliver a packet from source to destination. The basic characteristics of IP are, first of all, it is connectionless. That means that no connection with the destination is established before sending data packets. It is also unreliable, and this characteristic is also called best effort. By unreliable, it doesn't mean that it's a poor data communication protocol. It means that there is a lack of capability to manage and recover from undelivered or corrupt packets, which can be translated to a characteristic in which delivery is not guaranteed. And IP is also media independent. Operation is independent of the medium carrying the data. However, there is a characteristic that the network layer does consider, which is the maximum size of the PDU that each medium can transmit. This is also called maximum transmission unit. IP encapsulates or adds into the transport layer segment in an IP header. This header is used to deliver the packet to the destination host. Like we said, there are two versions of IP version 4 and IP version 6. IP version 4 has been used since 1983, and it has, the IP version 4 packet has two parts principally. The first one is the IP header, which identifies the packet characteristics, and the second one is the payload, which contains the layer 4 segment information and the actual data. There are also some significant fields of the IP header that include version, which is a 4-bit binary value that identifies the IP packet version. For the version 4, this field is always set to 0100. The other field is differentiated services, that is also called type of service field. This is an 8-bit field used to determine the priority of each packet. There is another field which is called time to live, which is an 8-bit binary value that it is used to limit the lifetime of the packet, and it is specified in seconds but is commonly referred to as hop count. The protocol field is an 8 binary value that indicates the data payload type that the packet is carrying, which enables the network layer to pass the data to the appropriate upper layer protocol. And there is also another field called source IP address and destination IP address. These two fields are represented by 32-bit binary value, and obviously they represent the destination and the source of the packet. There are other fields used to identify and validate the packet, like internet header length, which is a 4-bit binary value that identifies the number of 32-bit words in the header. The minimum value for this field is 5 and the maximum value is 15. And there is another field that is used to validate the packet that is called total length, which is also referred as packet length, which is a 16-bit field that defines the entire packet size. The minimum length for this field is 20 bytes and the maximum is 65,535 bytes. Finally, we have the header checksum, which is a 16-bit field used for error checking, and if the values do not match, the packet is just discarded. We have to consider that sometimes when you are willing to reach a medium that has a smaller max transmission unit, you need to fragment your packet. When this happens, the IP version 4 packet uses special fields to keep track of those fragments. These special fields are identification, that is a 16-bit field that identifies a fragment of an original IP packet. There is also flags that are 3-bit value that identifies how the packet is fragmented, and also a fragment offset, which is a 13-bit field that identifies the order in which to place the packet when reconstructing it. Even with changes, IP version 4 has some issues. These issues are IP address depletion, that it is due to the increased needs for new addresses, Internet routing table expansion, which produces a bigger consumption of memory and processor resources, and also lack of end-to-end connectivity, because through network address translation, multiple devices share a single public IP address. Because of these issues, the version was improved, and that is where IP version 6 appears. This version was presented in the early 1990s, and some improvements include increased address space, because IP version 6 addresses are based on 128-bit hierarchical addressing as opposed to IP version 4, which was only for 32 bits. Also, it is an improved packet handling because the IP version 6 header has been simplified with fewer fields, obviously improves the packet handling, and also eliminates the need for NAT. NAT is the network address translation, because with IP version 6 addresses there are a large number of public addresses, there is no need for using network address translation. And also there is the integrated security. IP version 6 natively supports authentication and privacy capabilities. The simplified header of an IP version 6 doesn't include some fields of the IP version 4, but there is a new field that is added, which is called flow label. This generates some advantages, like better rounding efficiency, no requirement for processing checksums, simplified and more efficient extension header mechanisms, and this flow label field helps for per flow processing with no need to open the transport inner packet to identify the various traffic flows. The IP version 6 fields are version, which is also a 4-bit number that identifies the packet version, and in this case the number is set to 0110. The other field is traffic class, which is a 8-bit field, and it's equivalent to the DS field of an IP version 4. Flow label, which is a 20-bit field. This is a new field that provides a special service for real-time applications. For example, it can be used to inform routers and switches to maintain the same path for the packet flow. The payload length is a 6-bit field, which is equivalent to the total length field in the IP version 4. Next header is an 8-bit field, which is the equivalent of protocol field, and this field enables the network later to pass the data to appropriate upper layer protocol. Other field is hop limit, which is an 8-bit field that replaces the IP version 4 TTL field. And when this value reaches to 0, the sender is notified that the packet was not delivered. And then we have the source and destination addresses, both consisting of 128 bits. Another role of the network layer is to direct packets between hosts. It is important to mention that a host can send a packet to itself for testing purposes by sending a packet to a special IP version 4 address. It can also send packet to a local host, that means another host that shares the same network address, or it can send a packet to a remote host. This is a host on a remote network. In local networks, devices are interconnected together using an intermediate device that provides interconnection between local hosts. If a host is sending a packet to a device that is configured with the same IP network as the host device, the packet is simply forwarded out through the intermediate device to the destination device directly. If you want to go beyond the local area network, there are remote hosts. When a device sends a packet to a remote destination device, a router is needed, and is needed because it identifies the best path to a destination. This is also called routing. It is important to mention that the router connected to the local network segment is referred to as the default gateway. The default gateway, which is most often a router, maintains a routing table. What is a routing table? A routing table is a data file that is stored in the RAM, and it is used to keep the route information about directly connected network, as well as entries of remote networks the device has learned about. A router uses the information in the routing table to determine the best path to reach those destinations. The local table of the host typically contains direct connection, local network route, and local default route. The default route represents the routes that packets must take to reach all remote network addresses and is the IP address of the network interface of the router that is connected to the local network. It is important to note that the default gateway is only used when a host must forward packets to a remote network. If you are just sending information on a local network, you don't need a default gateway. To display the host routing table on a Windows host, the route print or netstat r command can be used. Entering one of these commands displays 3 sections related to the current TCP/IP network connections, which are interface list, which lists the MAC addresses and assigned interface number of every network capable interface on the host, the IP version 4 route table, which is a list of all known IP version 4 routes, including direct connections, local network, and local default routes, and also IP version 6 route table, which is a list of all known IP version 6 routes. The output is divided into 5 columns, which identify the network destination that lists the reachable networks, netmask, which is a subnet mask that informs the host how to determine the network and the host portions of the IP address, the gateway, which is address used by the local computer to get a remote network destination, interface, which is an address of the physical interface used to send the packet to the gateway that is used to reach the network destination, and metric, which lists the cost of each route, and this is really important because it is used to determine the best route to the destination. Now for the IP version 6 route table, this differs from the IP version 4 in column heading and also in format. In this case, the table row displays 4 columns. The first one is the if column that lists the interface number of the interface list section of the netstat R command. It is also a column for metric, which lists the cost of each route to a destination. And in here you have to remember that lower numbers indicate preferred routes. There is another column which is called network destination, which is a list of the reachable networks, and also gateway with a list of addresses used by the local host to forward packets to a remote network destination. Now we're going to talk about the router packet forwarding decision. When a host sends a packet to another host, it will use its routing table to determine where to send that packet. The routing table of a router stores information about directly connected routes and remote routes. The routing table of a router is really close to a routing table of a host. They both identify the destination network, metric associated with the destination network, and the gateway. On a Cisco router, the show IP route command can be used to display this information, the routing information. When a packet arrives at the router interface, the router has to examine the packet header to determine the destination network. If this destination network matches a route in the routing table, then the router forwards the packet using the information that it obtained in the routing table. If there are 2 or more possible routes to the same destination, the metric is used to decide which route appears on the routing table. 2 routing table entries are automatically created when an active router interface is configured with an IP address and subnet mask. The entries contain the following information. We have first the route source that identifies how the route was learned. And for directly connected interfaces, there are 2 route source codes. The first one, you used a C letter to identify a directly connected network, or you use an L to identify that it is a linked local route. There is another type of information which is called the destination network that identifies the address of the remote network. Also, we have outgoing interface that identifies the exit interface to use when forwarding packets to the destination networks. As with directly connected networks, the route source identifies how the route was learned. And common codes for remote networks include a letter S, which identifies that the route was manually created by an administrator to reach a specific network, and this is known as a static route. It also uses a letter D to identify that the route was learned dynamically from another router using the Enhanced Interior Gateway Routing Protocol, or it uses a letter O to identify that the route was learned dynamically from another router using the Open Shortest Path First. For remote networks, the information displayed in the routing table contains the route source that identifies how the route was learned, the destination network that identifies the address of the remote network, and administrative distance that identifies the trustworthiness of the route source, metric, which is the value assigned to reach the remote network, next hop, that identifies the IP address of the next router to forward the packet, route timestamp that identifies when the route was last heard from, and outgoing interface that identifies the exit interface to use to forward a packet toward the final destination. Talking a little bit more about the next hop address, this is the address of the device that will process the packet next. For a host on a network, the address of the default gateway is the next hop for all packets that must send to another network. Networks directly connected to a router have no next hop address, because a router can forward packets directly to hosts on these networks using the designated interface. Now we're going to talk about routers. Cisco routers are designed to address the needs of branch, which are small business, teleworkers, and medium-sized branch sites. Also, WAN, that are large business, organization, and enterprises, but also service provider, which are large service providers. Regardless of their function, all routers require operating systems, central processing units, random access memory, and read-only memory, just like a computer. Also, a router has a special memory that includes flash and non-volatile random access memory. The Cisco Internetwork Operating System is the system software used for most Cisco devices regardless of the size and type. A router has 4 types of memory. The first one is random access memory. This memory is principally used for running Cisco IOS, running configuration file, also known as the running config, saving the IP running table that is used to determine the best path to use to forward packets, storing the ARP cache, which contains the IP version 4 address to MAC address mappings, and containing a packet buffer. This buffer temporarily stores packets when received on an interface or before they exit an interface. Cisco routers also use dynamic random access memory that stores the instructions and data needed to be executed by the CPU. The other type of memory is the ROM memory, read-only memory. This memory stores the boot-up instructions, the basic diagnostic software, and a limited version of the iOS just in case the router cannot load the full feature. The third type of memory is the non-volatile random access memory. This memory is used as permanent storage for the startup configuration file. And finally, the flash memory that is used as permanent storage for the iOS and other system-related files. The general hardware components of a router are CPU, NVRAM, SDRAM, Advanced Integration Module, Shield for WAN interface card, power supply, and a fan. A Cisco 1941 includes the following connections: 2 console ports for the initial configuration and command line interface management. They are usually an RJ45 and a mini USB. Another connection is the aux port, which is an RJ45, and it is used for remote management access. And also 2 gigabit LAN interfaces for LAN access, and enhanced high-speed WAN interface card. This is used to support different types of interface modules. The Cisco 1941 ISR also has 2 4 GB storage slots to support expanded capabilities and 2 USB ports. The connections on a Cisco router can be grouped into 2 categories: the management ports, which are the console and auxiliary ports used to configure, manage, and troubleshoot the router, and the in-band router interfaces, which are the LAN and WAN interfaces configured with an IP address to carry user traffic. For accessing the client environment on a Cisco router, the most common methods are console, that uses a low-speed serial or USB connection to provide direct connect out-of-band management access to a Cisco device. We also have Telnet or SSH. These 2 methods are for remotely accessing a CLI session across an active network interface, and we have the aux port that is used for remote management of the router but using a dial-up telephone line and a modem. In addition to these ports, routers also have network interfaces to receive and forward IP packets. Each interface must be configured with an IP address and a subnet mask of a different network. These interfaces can be grouped in two categories: the Ethernet LAN interfaces and the Serial WAN interfaces. When a router is boot, it loads the following files into the RAM. First, the iOS image file, and then the startup configuration file. This file contains commands that are used to initially configure a router and create the running configuration file that is going to be stored in the RAM. All configuration changes are stored in the running configuration file and then are implemented immediately by the iOS. There are three major phases to the boot up process. The first one is to perform the post and load the bootstrap program. The post is the acronym of Power on Self-Test, and it is used to test the router hardware. After it, the router executes the bootstrap program. The main task of the bootstrap program is to locate the Cisco iOS and load it into the RAM. The second phase is to locate and load the Cisco iOS software. The iOS is typically stored in flash memory and then it's copied into RAM for the execution of the CPU. And the third phase is to locate and load the startup configuration file or enter setup mode. The bootstrap program then searches for the startup configuration file, and the running configuration file contains interface addresses, starts routing processes. It also configures router passwords and defines other characteristics of the router. It is important to mention that if the iOS image is not located when locating and loading the Cisco iOS, or if the startup configuration file does not exist when locating and loading the configuration file, the router may look for this information through a trivial file transfer protocol. To verify and troubleshoot some basic hardware and software components of a router, you can use show version command, which displays information like iOS version, ROM bootstrap, location of iOS, type of CPU, amount of RAM, interfaces and amount of NVRAM, and flash. The last line of the show version command displays the current configure value of the software configuration register, and this will help in the password recovery. Now, talking about the configuration of a Cisco router, switches and routers have identical initial configuration steps when implementing them in a network. The steps that should be completed are: first of all, assign a device name using the hostname global configuration command. Then it will be to set the passwords. In this part, it includes to secure privilege exit mode, secure exit mode access, secure virtual access similar to executing exit access mode, and use the service password encryption. The third step is to provide legal notification using the banner MOTD, message of the day, and then you have to save the configuration using the copy run start command, and finally to verify the configuration using the show run command. For a router to be reachable, it must be configured. To enable a specific interface, you have to enter interface configuration mode using the interface type and number global configuration mode command. There are many types of interfaces available on Cisco routers, like the Gigabit Ethernet or Serial. To enable a router interface, you have to configure the IPv4 address and a subnet mask, and also you have to activate the interface. By default, LAN and WAN interfaces are not activated. The interface must be activated using the no shutdown command, and the interface must also be connected to another device like a hub, a switch, or another router for the physical layer to be active. To verify interface configuration, the most useful command is show IP interface brief, and the output generated displays all the interfaces, their IP address, and their current status. To verify connectivity from the interface, you can use the ping command that we have used a lot of times, And other interface verification commands include show IP route, show interfaces, and show IP interface. Most routers have a minimum of 2 interfaces. Each interface is configured with a separate IP address in a separate network. For an end device to communicate over the network, it must be configured with the correct IP address information, and this includes the default gateway address. The default gateway is only used when the host wants to send a packet to a device on another network. A default gateway is used by all devices that require the use of a router to determine the best path to a remote destination. End devices require the default gateway, and so intermediate devices such as the Cisco iOS switch. For this, you will have to configure the IP address and also the default gateway with special commands that are shown in the figure, and with this you will be able to transmit information. And well, this is the end of the video. I hope you enjoyed it, and thanks for watching.